In Chapter 7, we'll start looking at alkyl halides, which will be our first reactions that we will begin with. And we've looked at mechanisms a little bit in Chapter 6, and we'll reinforce those in Chapter 7 and in Chapter 8. So the first ones that we'll look at are nucleophilic substitution reactions. So a substitution reaction is one where a group of atoms is replaced with another. So in this reaction here, X is getting replaced with Y, so this is a substitution reaction, which we'll see in Chapter 7. And if X goes away altogether and is replaced with a double bond, this is an elimination reaction, which we'll see in Chapter 8. So we have a reaction here. This is 2-chloropropane. We add nucleophile, which is thiol. So this is a nucleophile. This is our electrophile. The nucleophile will give the electrophile a hug before the leaving group leaves, which is chlorine. So if you follow those electrons, this is going to form a new bond here, and the chlorine will leave. And you get Cl-. To encourage a substitution reaction, you must have a good leaving group, and the leaving group has to fulfill two criteria. The electronegative leaving group has to create a partial charge on the site of the attack to attract negative charge of the nucleophile. The leaving group must be able to stabilize the electrons it leaves with. So what that means is the nucleophile has to be negative, electrophile needs to be positive or partially positive to attract the nucleophile, and then the leaving group must be able to support and stabilize the negative charge. So in this case, we have the chlorine leaving. That would form this and the Cl-, which is stabilized because chlorine is an electronegative atom. So what you can see in this electrostatic map here with the fluorine, chlorine, bromine, and iodine, as the size of the atom grows, it is more electronegative for here, or can better support the charge because of the size of the molecule. Really good leaving groups are conjugate bases of strong acids. So the strongest acids are HI, HBr, HCl, and this tosic acid. So the best leaving groups are I-, Br-, Cl-, this sulfonate, and water is a good leaving. We also have other sulfonate ions that can be leaving groups. This one here is called a tosylate. You can have a mesylate, and a triflate. So this has CF3 instead of a CH3. This is a triflate. These are all good leaving groups. The bad leaving groups are ones that cannot stabilize the charge very well. Bad leaving groups are F-, OH-, and ethoxy-, tert-butoxy- or tert-butoxide, and an NH2-. So even though these atoms are electronegative, it really can't stabilize the charge that well, especially compared to larger electronegative atoms. So these are worst leaving groups. And these are the best. The amount of branching at the alpha carbon affects the reaction mechanisms, and there's three types of alkyl halides. The alpha carbon is the carbon that the halogen is immediately connected to. If the carbon that your halogen is bonded to has only one other, this is a primary alkyl halide. This carbon is bonded to two other carbons, this is secondary. This is tertiary. Alkyl halides are compounds where a carbon group is bonded to a halogen, And when we're naming them, you first identify the parent chain. So the parent chain here is cyclohexane. Then we're going to identify and name the substituents. This is an isopropyl. This is a bromo. Then we're going to assign a locant number to each substituent. This would be 1, and this is 2, just for alphabetical purposes. And then we put the name together. So we have 1 bromo, 2 isopropyl, cyclohexane. So again, the halide group here is what's different, and that's the key substituent we're going to name and locate. Okay, so to name this one, the parent chain is 3 carbons. So we have propane, B2-chloro, propane. This is 5 carbons. We have a methyl and a bromo. Bromo comes first alphabetically. All right, and this is numbered for us. We have a bromo at 5, but you have to determine the stereochemistry if it's indicated. This happens to be 1, 2, 3. This is R, so it'll be R, 5 bromo, 2, 3, 3, trimethyl heptane. Okay, so to name these ones, 1 bromo, 2 isopropyl, cyclopentane, and this one is 2,2-dichloro, 3-methyl hexane. So by the end of the semester, you'll be able to do several of these reactions, and by the end of the year, you should be able to do all of them. Okay, so in an SN2 reaction, every nucleophilic substitution reaction, either SN1 or SN2, is going to involve a nucleophilic attack or hug and the loss of a leaving group. But it's not always going to happen in the same order or at the same time. So in this first one, we recognize the loss of a leaving group, and what results is the carbocation plus Br minus. And this nucleophilic attack, when that happens, you get the bromine to add there. So every nucleophilic substitution reaction is going to involve a nucleophilic attack or a nucleophilic hug, and then the loss of a leaving group. In an SN2 reaction, it's a concerted mechanism, which means that the bonds are being broken as they are being made. So it's all happening at the same time. The rate of the reaction depends on the concentration of the substrate and also the nucleophile. So the rate can be described as K times the concentration of substrate and the nucleophile. So in an SN2 reaction, the S stands for substitution, N stands for nucleophilic, and the 2 stands for bimolecular, because the rate depends on the substrate concentration and the nucleophilic concentration. So in an SN2 reaction, there's 2 steps that are happening at the same time. The first thing that happens is the nucleophilic attack. And while that bond is forming, we get a loss of leaving group, and this bond is breaking. So this bond is formed with the nucleophile, and then the leaving group takes the electrons with it. The nucleophile attacks hugs from the back side because the approach from the same side as the leaving group is disfavored due to sterics. So the leaving group is going to be in the way. So when this nucleophile comes, the bromine here is large. So you can see here, if it tried to do a front side attack, this is slowed by sterics. So it's much easier to get in over on this side. This nucleophilic attack will come in over here and form a bond there, and then there is your leaving group leaving. Again, this is the nucleophile, this is your leaving group, this is your electrophile. So you get that nucleophilic attack. So when that happens, we form a bond with the SH plus Br. So before this stereochemistry was S, and now it is R. You can look at this orbital drawing here. If you tried to do a front side attack, it would be very difficult for that molecule to get in here because there's electron repulsion and also sterics. So if you recall, our nucleophile is negatively charged and the negative doesn't want to come in where it's already negative, and that's why it comes in from the backside, which is electrophilic. If we're just looking at this again, we have the sulfur is coming in from the back here, so that's the nucleophile, this is our electrophile, this is our leaving group. Sulfur is going to come in from the back side where it can get more easy access, and then the bromine leaves, and this is the transition state where the bonds are forming as they're being broken at the same time, and then we get an inversion of stereochemistry. So things that are reactive are things that have less sterics or less bulk. So this methyl is 1,000 times more reactive than the secondary. Primary is 100 times more reactive, and this one is too slow to measure. So this is most reactive. This is least reactive. Draw the product for the following SN2 reactions. A couple of things that I'm going to do when we're going through these reactions the first couple times is I'm going to look for the nucleophile, look for the electrophile, and then also look for the leaving group. So this is my nucleophile. If this is positive sodium, this is negative. So this is my nucleophile. Bromine is partially negative, so the carbon attached to it's partially positive. This is my electrophile. And bromine is the leaving group. In an SN2 reaction, remember we have two types of arrows or mechanisms going on. The first is the nucleophilic attack, followed by loss of a leaving group. So this is the nucleophilic attack or hug, and then this is loss of leaving group. So OH is going to get added, and since we attacked from the back side, we're going to switch the stereochemistry here to OH, which is dashed now. And then there's Br minus. All right, in this reaction, Na is plus still, Cl is minus. This is my nucleophile. This is the electrophile. Here is my leaving group. Nucleophile will attack the electrophile, and then we have a leaving group leaving. So this is nucleophilic attack, and that's loss of leaving group. And that becomes wedged and replaced with Cl, and then we lose I minus. So we can look at kinetic data with this. The starting compound in this reaction is a Cn minus, and we're going to add bromomethane. The potential energy of the reaction starts here, and it needs to overcome the activation energy while it's forming the transition state. With the Cn. So this is the transition state. And then after the bond is formed, we have a big dip in energy and the product is more stable. So we have an N, C, CH3 plus Br minus. So the inversion event as the 5 atoms gather around the C here can be thought of as an umbrella in high winds. Or you can see this here, if you have this umbrella facing the wrong way, your handle is here, and you have a new nucleophile coming in, and then once it forms here, and then we're flipping the whole reaction. So that's how the stereochemistry gets inverted. This is called the Walden inversion. And this was the first chemist who observed this occurring. So because they're coming in from the backside, the SN2 reactions, it's very sensitive to sterics and works better with less hindered alkyl halides. And we can see the energy diagrams for these as well. So this is an SN2 reaction that can happen with a methyl substrate. This is one with a primary substrate. And this is with a secondary substrate. So methyl does not require much energy to get over the activation energy barrier. Primary needs a little bit more, and secondary is a bit higher than that. So less bulk equals faster reaction. Draw the transition state for the following reaction. So we start here, we just draw the shape of it in general. We start with the Br, and then up here is the Br with the OH. So this is being broken as that's being made, and then the new product is there. Nucleophilicity is the rate at which a nucleophile will attack a suitable electrophile. If you have a strong nucleophile, that means a fast reaction. If you have a weak nucleophile, that's going to have a slow reaction. So for SN2, you must have a strong nucleophile. So strong nucleophiles include the halogens, thiols that are charged, or are thiols, hydroxide, alkoxides, and C minuses. Things that are weak nucleophile include water and alcohols. So if you're looking at what's the difference here, all of these strong nucleophiles have an actual negative charge. The weak nucleophiles are neutral and are just partially negative. For an SN2 reaction, the solvent that you run the reaction in is also important. SN2 reactions usually have ionic nucleophiles like we saw, and they also have ionic leaving groups. So everything is going to have a negative charge here. So what you want is a polar protic solvent to solvate or support the ionic species. So we know what polar means. That just means that there is a difference in electronegativity in the bonds in the solvent, but aprotic means that it does not contribute any protons. So some polar aprotic solvents include acetone, you can see the dipole going from the carbon to the oxygen. We have dimethylformamide, or DMF. There's HMPA. And that stands for hexamethylphosphoramide. We also have dimethyl sulfoxide, or DMSO. So this looks like acetone but has a sulfur there. And then the last one is acetonitrile. Which can be abbreviated ACN. So usually these polar aprotic solvents for some reason tend to have acronyms. So we have acetone except for that one, DMF, HMPA, DMSO, and acetonitrile. So these are all polar but don't contribute a proton. Protic solvents are polar, but they do contribute a proton. So these include water, alcohols, ammonia, and acetic acid. So these can all contribute a proton, which means that they also have acidic protons, and that makes it a polar protic solvent. So SN2 ones favor polar aprotic solvents. So again, a polar protic solvent can donate a proton, and in a polar protic solvent, that can stabilize cations and anions. If you had sodium and chloride ions floating around, the polar protic solvent can support both of them. So the lone pairs on the oxygen are stabilized by the sodium cation. The hydrogens are supported by the chloride ions. In a polar aprotic solvent, that stabilizes only the cations. It does not stabilize the anion, which is going to be our nucleophile. And we don't want the nucleophile stabilized because it won't react as quickly. So if you have a negative charge that's not being stabilized, it's going to look that much harder to find the electrophile to react. So if we don't stabilize the anions, that makes them more nucleophilic, which is better for the reaction. Okay, so unstabilized nucleophiles in aprotic solvents have higher energy. So in polar aprotic solvents, again, the nucleophiles are much more reactive, so they're higher in energy, which makes this energy hump here that much smaller. So it lowers the activation energy. So we can look at the different effects of solvents on the right here. So if you have an I- nucleophile in methanol, which is polar protic, that is something like 43. If you change that to DMF, which is your polar aprotic solvent, that increases the reaction rate to 6,500 or times 150. For F- is that if that's your nucleophile, this is very, 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 very slow because it can hydrogen bond. The F can hydrogen bond in methanol. But if you do it in a polar aprotic solvent, that increases the speed of the reaction by 82 million times. So it is very important to use the right solvent to do your SN2 reactions.